As we saw in the video for the decimation cipher, the multiplicative inverse of an integer modulo some other integer was really important. So what we're going to do is we're going to look at that more closely. Then we're going to determine exactly when a number a has a multiplicative inverse mod n, and we'll do it in a way that's relatively easy to check. Then we're going to use this to determine appropriate keys for decimation cipher so we don't run into the same trouble as we did choosing a key of 4 for the decimation cipher. Alright, so I want to look more closely at why 4 does not have an inverse mod 26. What we did before was we just listed all the numbers times 4 and see if we ever got 1, and we didn't, and then we sort of threw up our hands and said, nope, doesn't work. But I want to look at more closely about why that's true to see if we can come up with a better way than just looking at all the possibilities. Well, if we're trying to find an inverse, here's what we want. We want to multiply 4 by some number, I'll call it x, 4 times x, so that when we take that number mod 26, we get 1, right? That's exactly what it means to be a multiplicative inverse. So another way of saying that, if you want to look at it in terms of congruence, it says that if we look at the actual number 4x, not mod 26, but just the number, that should be congruent to 1 mod 26. And if you remember what that means that 4x, well, 4x could equal 1, or it could be off by, well, there are 26 days in a week if we're mod 26, right? Any multiple of 26 it could be off by. All right, so that's n weeks, 26 days a week. So let's see what that implies. So I'm going to rewrite that in a slightly different way. I'm going to write the 4 as 2 times 2. So you get 2 times 2x on the left-hand side. And then I'm going to write 26 as 2 times 13. And notice that each of those terms, the 2 times 2x and the 2 times 13n, each have a factor of 2. And then you're adding 1 to the number on the right side of the equation. Well, let's look at the left side. Left side is 2 times 2x, which is an even number. An even number is exactly any number times 2. But if you look at the right side, 2 times 13n is a real number, but then we're adding 1 to it, which actually makes it an odd number. And so what we're saying is if we want to find a multiplicative inverse of 4, what we need is some even number that's also equal to an odd number, which is impossible. So that tells us that 4 does not have a multiplicative inverse mod 26. And notice we were able to figure that out without having to look at all the numbers times 4 and say, oh yeah, it didn't work. And it also sort of explains why when we were taking all those numbers mod 26 that we never got any odd numbers. We only got even numbers. All right, so let's try another possible number that we can take a multiplicative inverse. Does 13 have an inverse mod 26? Now 13 doesn't have the same issue of being an even number, and so maybe this one's going to be okay. So let's try it. So again, for it to have an inverse, we need to have some number x. When we multiply 13 times x and take it mod 26, we get 1. And again, if we want to interpret that in terms of congruence, that tells us that 13 times x is congruent to 1 mod 26. And again, we write what that means, right? That means 13x is equal to 1 plus some number of weeks, right? Again, a week is 26 days. So 26n tells us that's n weeks. So now what I'm going to do, instead of looking at the number 2, I'm actually going to look at the number 13, because we have 13x on the left-hand side, but notice that 26 is equal to 13 times 2. So I can write that 26n as 13 times 2n. And now I'm going to do the same kind of analysis with left side of the equation, right side of the equation. Except this time on my left side, that's going to be some multiple of 13. No matter what x is, it's going to be some multiple of 13. 13, 26, 39, 52, etc. But on the right side, that 13 times 2n is itself a multiple of 13. And if you add 1, that says it's 1 more than a multiple of 13. And now we've got to ask ourselves, well, what's a number that is a multiple of 13, but also 1 more than a multiple of 13? Well, there isn't any such number, right? It's impossible for a multiple of 13 and 1 more than a multiple of 13 to be equal, which actually says that 13 does not have a multiplicative inverse mod 26 either. So this is really troubling, right? So there are potentially tons of numbers that don't have a multiplicative inverse. So let's see if we can analyze this to see which numbers have multiplicative inverse. So what was troublesome with 4 was that 4 and 26 were both a multiple 2, so we had that odd-even problem. And actually, we had a similar problem with 13 because 13 and 26 are both multiples of 13, and that caused a problem with multiples of 13. So in general, if you have A mod n, we get the same contradiction anytime when A and n have a common divisor that is not 1. Remember, we can't avoid having a common divisor of 1. 1 divides evenly into everything. But if they happen to be numbers that don't have common divisor, that's the only way we can escape not having a multiplicative inverse. So here's the theorem that we get. If A and n are some integers, then we know that A has a multiplicative inverse mod n exactly when the GCD of A and n equals 1. That's exactly what has to happen in order for A and n not to have any common divisors other than 1. And of course, we had a name for this back in the old days being, what, a couple days ago? That means it happens precisely when A and n are relatively prime. So, let's get away from 26 for a while and look at multiplicative inverses mod other numbers. So does 5 have a multiplicative inverse mod 13? Well, if we look at the GCD of 5 and 13, yeah, it does. Because, well, one way of looking at it is if we look at the GCD of 5 and 13, they share no factors except 1. In fact, they're both distinct primes, so 1 is the only one that we get. But also, if we actually wanted to search around for a multiplicative inverse, 5 times 8 is 40, and 40 is mod 13 is equal to 1. So that tells us that 5 times 8 is mod 13 is 1, which means that 8 is the multiplicative inverse of 5 mod 13. What about 10 mod 15? Well, no, and that's we can think of that in two ways, right? First of all, we can think of it as, well, the GCD is 5. 5 is not 1, and so 10 can't have a multiplicative inverse mod 15. But also, we get the same thing, a similar thing that we got with 4. Remember that they had all even numbers? With this one, you have to check this, but all 10 times x, all multiples of 10 mod 15 are going to be a multiple of 5. And since they're going to be a multiple of 5, there's no way that you're ever going to get 1. All right. So, what does this mean about keys of the decimation cipher? Getting back to that one. Well, it means that if we have an encryption key, it must be relatively prime with 26. Remember, the problem with 4 and with 13 is they shared factors with 26 that weren't 1. And then the decryption keys, remember, are going to be the multiplicative inverses of those encryption keys. And so let's do one more example just to show you how to do this. So if our encryption key is 15, first thing we're going to do if we want to be able to decrypt our messages is figure out when 15 times a number is congruent to mod 26 is equal to 1. So we're just going to do it the same way. We're going to keep on trying. Again, you may think, well, you just did 1 to 9 there, Darren. What's wrong with you? Well, if 1 to 9 doesn't work, we'll go to 10 to, 10 to 18, and then 19 to 26 until we can find one. We know we can find one because 15 and 26 do not share any common factors. If we can't, then I guess we'll just have to cry. So let's see. So we're going to multiply each of those by 15 to see what we get. 15, 30, 45, 60, etc. Those are just all multiples of 15, excuse me. But the next thing we want to do is we want to mod those out by 26 to see if we get any 1s. And lucky us, look at there, right below the 7, right below the 7 and the 105, we get a 1, which means that when we multiply 7 times 15, we get 1 mod 26. And that tells us that 7 is the multiplicative inverse of 15 mod 26. Which that makes it the decryption key. And remember, what I mean by decryption key is if you have some ciphertext and want to bring it back into plain text, what you do is you multiply the numerical value of each of the letters in the ciphertext by 7. And that will take you back to the plain text. If you have plain text, you multiply by 15 to get to the ciphertext. If you have ciphertext, you multiply by 7 to get back to the plain text. Alright, so now I think you're ready to work on multiplicative inverses, and that's on the PDF file included with this video.